So welcome everybody to our weekly seminar that we host at UKZN. This week we have Dr. Elena Caviglia, I hope I pronounced that correctly, joining us. Elena recently completed her PhD at the University of Leicester in England, where she was supervised by Professor Frank Neumann. I had actually met her just more than a year ago when I visited Italy to work with Prof. Frank Neumann, and I met her when I was visiting the University of Pavia and we chatted for a bit. Currently, she is based at Stellenbosch University, where she is pursuing a postdoc under the supervision of under the host Prof. Surjective. And her interest lies a lot in category theory, and she considers applications in geometry, topology, as well as algebra. Today, she's going to be talking to us a little bit about the work she's done. And so we're going to be learning about factorization systems in categories and double categories. We're eager to hear more.
So first of all, thank you very much for giving me the opportunity to speak here. I'm very happy to be at UKZN, and I look forward to working with all of you. Today, I'm talking about factorization systems, and in particular, the talk is based on a project, an ongoing project that started with the Adjoint School. The Adjoint School is a research school that is held every year in a different place, and this year it was in Oxford. So there are different research groups. Each group is led by a mentor, and there are teaching assistants and students. They all work together for a week, and then the project continues with papers and a fruitful collaboration. So my group was led by Professor Lorette Pronk, who is coming here at UKZN in December, so you'll meet her. Luca and I were the teaching assistants of the project, and the other 4 people are our students. So we are all working together on factorization systems on double categories. But before we go into the details of that, let's first think about factorization systems and why they are important. There is this very famous theorem called Noether's first isomorphism theorem that it has various forms, can be written for groups, vector spaces, and different algebraic structures. Here I'm presenting the one for vector spaces. So if we have two, say, real vector spaces, you can think also of other kind of vector spaces, of course. And you have a linear map F between them. Then the following things follow. You can construct a subspace of the domain V that is called the kernel of the linear map. And it's the space of all elements of V that are sent into the 0 of W by F. Then you can construct another subspace that is the image of the linear map. So this is a subset of the codomain W and is given by all the elements of W that are image of something in V. And then there is this very important isomorphism between the quotient of the domain with the kernel and the image. And the idea between these is that if we have the linear map F, we can factorize this map into a composite. The first part will be a projection from the domain to the domain mod kernel. The second part will be this isomorphism here, so a bijective linear map. And the third part will be an inclusion of the image in the codomain W. So the idea is that given any linear map, we can factorize it into a composite of simpler maps with better properties. So this, for example, is surjective, and this is injective. And since the one in the center is bijective, we can also consider the composite of these two, and this is still a surjective map. So we can rewrite the factorization a bit has these and these, where the first is surjective and the second is injective. And so the idea of a factorization system is the idea of identifying special kinds of maps, such that every time we have a map, we can factorize it as a composite of these maps of special kinds with better properties. And we want to view these in a categorical context. So first, we notice that this result also holds for groups, rings, and modules. So we can kind of think about generalizing this result to categories. But let's start from the basis. What is a category? So a category C is given by this data. We have a set of objects of the category. We can call them A, B, C, right? Then we have arrows between these objects. So for example, we can have an arrow called F from A to B, another called G from B to C, and maybe another one H, still from A to B. So what is the idea? This is kind of the same idea of a graph, where the objects are the nodes of our graph, while the arrows, that are also called morphisms, are the edges of our graph. But the idea is that these edges have an orientation. So we don't just say there is an edge from between A and B, we say that it goes from A into B. And then we can also have multiple edges from between the same nodes. So this should be like, I don't know how it's called in graph theory, but you can have multiple edges between two nodes. And then we have some special rules that we want for our graph. The first is that we can compose arrows. So if we have an arrow from A to B that we call F, and then we have another one from B to C that we call G, there is another arrow in the category that is called G composed with F, and it goes from A to C. And the idea is that we are composing arrows, just as we compose functions between sets, for example. And moreover, for every object, there is a special arrow that is called the identity of the object, and it goes from the object to itself. So it's kind of a loop in the graph. And it plays the role of the identity. So if we compose, for example, if we put identity of A and then F, the composite is still F. So it acts as an identity. And we also have rules. For example, our composition, we want it to be associative. So if we want to compose F and G and then compose it with another morphism H, this is the same as composing G and H first and then pre-compose with F. So the composition is associative. And categories arise everywhere in mathematics, but not only in mathematics. So let's see some examples. First example is the category of sets. So objects are sets. And what are arrows between sets? They are functions. So every time we think of a category, we have some objects. Maybe we can think of the more natural way of interrelating these kind of objects, and we can take those as morphisms. So for sets, we have functions. Then we can construct a category whose objects are vector spaces, and now we want the morphisms to be linear maps. So they are not only functions, but they respect the structure of vector space. And then we can have other algebraic examples. For example, we can have groups and group homomorphisms, so rings, R modules, and whatever you can imagine. We can also have more geometrical, topological categories. For example, we can have a category top of topological spaces, and now the arrows are continuous maps between them. But then we also have special kinds of categories that are maybe more degenerate in some sense. For example, we can consider just a set S, and we can view it as a category in which the only arrows are identities. So there are no other arrows between the objects of the set, the elements of the set in this case. Or we can have the category of the open subsets of a topological space. So if we take a topological space X, and we consider the open subsets of X, together with the inclusions, we get the category. What do I mean by inclusion? I mean that if we now take U and V to open subset of the topological space X, if one is included in the other, we have an arrow between them. Otherwise, if they are not comparable, we don't have any arrow between them. And in this way, we can construct a category. But then we can do something a bit more complicated. For example, we might want to consider the category whose objects are categories. And so now we want a way to go from a category to another. And this way is called a functor. So we can think of a functor as a function between categories. So it will be two functors, one that sends object in the domain category into objects in the codomain category, and one sends morphisms in the domain category into morphisms in the codomain category. And this functor will respect composition and identities. And we can do all kinds of things. For example, we can construct a category using functors. So now, for example, in this category, this is the category of functors between C of into set. Here, C of means I take a category and I reverse the morphisms. It's not really important, but this is the category whose objects are functors, and those morphisms are natural transformations. They are collectives. They are a way to go from a functor to another functor. And these kind of categories are, for example, important in geometry and studied in geometry. So before we go on, do you have any questions about categories? Good. So now let's see what are factorization systems in this context. So remember, we want to have a way to factor an arrow as composite of simpler arrows somehow. So if we have a category C, an orthogonal factorization system C is given by two classes of morphisms. One that we call the left class and the other that we call the right class. And as an example, we can think of them as being surjective maps and injective maps. Okay, this is our leading example. And then we have some properties for these classes of morphisms. The first is that they need to be closed under composition. So if we take two morphisms in the left class and we compose them, we get a morphism in the left class. In our example, if we take two surjective maps and we compose them, we still get a surjective maps. And the same for injective maps. Then we need to have that all invertible morphisms that are called isomorphisms are in both categories, in both classes. So if we have a morphism that has an inverse, then it needs to be both in the left and the right class. Then we want to be able to factorize morphisms. This was the main point of this whole thing. So if we have a morphism F from A to B, we need to be able to write it as a composite of a morphism in the left class and a morphism in the right class. And we need to be able to identify also this object that we want to put in the middle. And then we have another condition that says that left and right class are somehow orthogonal. We can think of it as a real spatial orthogonality condition. And the idea is that if we have a square like this, a commutative square, and by this I mean that the composite of F followed by R is the same, equal to the composite of L followed by G, if we have this situation. And moreover, the morphism on the left is in the left class, and the morphism of the right on the right is in the right class. We need to be able to uniquely determine a morphism from C to D that make these two triangle commutes. So we need to have that that LD is equal to F, and at the same time that DR is equal to G, and that this D is unique. Okay, so this is the definition. Let's see how it works in our example of vector spaces. So the class L is the class of surjective linear maps, while the class R is the class of injective linear maps. And we want to prove that this gives a factorization system. So, no, sorry, other direction. So we check the first condition. The two classes need to be closed under composition. And this is true because if we compose surjective linear maps, we get a surjective linear map. And same for injective linear maps. Then they need to contain all isomorphisms, so the invertible linear maps. And these are the bijective linear maps. And we know that if a map is bijective, is both surjective and injective. So this condition is also satisfied. Then we want to have a factorization, and this is given by Noether's isomorphism theorem for vector spaces. So we saw before that we can factor F as this composite, and the object in the middle is the image of F. So this is just the factorization we saw before. And now we need to have the orthogonality condition. How can we prove the orthogonality condition in this easy case? So we start from a square like this. We have that L is surjective and R is injective, because this is how we define our classes of maps. So we need to define this morphism, this D. So this needs to be a linear map. Given an object in Z, we define D of Z in this way. We know that L is surjective. So given Z, we can find an object V in V such that L of V gives that precise object, Z. And so we define D of Z as F of that precise V, so in this way. And if you think about it, this is saying that this triangle, this upper triangle commutes, because we have that D of L of Z is equal to F of V. Okay. To D of Z by construction. And then we also want these other triangle commutes, and we can check that with these assumptions, these commutes. So if we start from Z in Z, and we compute R of D of Z, this is R of F of V by definition of D of Z, right? And then now we have R of F of V, R of F of V, but R of F of something is the same as G of L of the same thing, because this bigger square was commutative. So we can replace R of F of V with G of L of V. And we had that L of V was Z, so we get G of Z. So if we look at the first and the last pieces of the equality chain, we get that R of D of Z is the same as G of Z. And this means that this triangle is commutative, which is what we want. And then we can also prove that this D is uniquely determined this way. And so now we have shown that that this is a factorization system on the category of vector spaces. But maybe we want to see different examples of factorization systems, so let's have a look. Oh, sorry, I scrolled on the wrong direction. We can take similar factorization systems on different categories. For example, we can do the same thing on set, the category of sets. So if we take surjective functions and injective functions, we get a factorization system. Or using again the other variations of Noether's first isomorphism theorem, we get the same kind of factorization system on the category of groups or rings or R modules, so different algebraic examples. Then we also have other more categorical examples. So we can define epimorphisms and monomorphisms. The notion is not really important, but the idea is that this generalizes the idea of surjective and injective for a category. And in some special categories that are called toposes, we get that this gives a factorization system still. And these categories are categories of sheaves, and they are important in geometry. For example, if you take a category of sheaves over a topological space, it has this form. They are much more general, but this is a specific example. So they are used, for example, in algebraic geometry and but also differential geometry. Then we can also have different factorization systems on the category of categories. So this time we are factorizing functors, and we can factorize functors in different ways. So for example, this first way says that we can factorize a functor as a pair of functors where the first one is a bijection on objects and the second one is a bijection on morphisms. So this is the idea. And then we have different kinds of factorization systems on this category of categories. Then we can have also factorization systems on categories of sheaves and many, many examples. So they are very useful in different areas of mathematics. And for this reason, our project was to define the same notion, but this time in the realm of double categories that are a special kind of two-dimensional category. So let's see what double categories are. So we have to think as double categories as two-dimensional categories in which we are able to have two different kinds of arrows, because in some practical situation, it can happen that we have some objects and we know two different ways of going from this kind of object to another of the same kind. And these two different ways are both important, and we want to study both of them. And they also interact in some sense. And the framework of double categories manages to capture this interaction between two different kinds of arrows. So let's see what a double category is. We still have objects, A, B, C, so on, and we still have arrows between objects. So F from A to B, G from C to D, and so on. But now we have a different kind of arrow that we call a pro-arrow, and we usually write it vertically to make it different from the arrow. So we can have a pro-arrow from A to C, and we write a pro-arrow with this different symbol, not to confuse it with an arrow, because it's a different kind of morphism. And now that we have arrows and pro-arrows, we can construct squares like this, where the horizontal edges are arrows and the vertical ones are pro-arrows. And we can also fill these squares with fillings that we call double sets. And this allows to capture the interaction between arrows and pro-arrows in our double category. Hopefully it will be clearer when we see examples of it. And then we are still able to compose, so we can compose arrows, we can compose pro-arrows, but we can also compose double cells. And we have two different ways of composing double cells. We can stack two double cells vertically, or we can do it horizontally. Sorry, horizontally or vertically. And they are both good compositions and they interact well with each other. So we have more freedom of working with these objects. And the compositions that we have are still associative unital and they are compatible with each other. So what are examples of double categories? So, okay, maybe before looking at examples, we can have a different way of encoding a double category that is an internal way. Might seem a bit more abstract and complicated, but it's useful when we work with double categories. So we can encode the same data of a double category in a different way as an internal category in the category of categories. So the idea is that we have two different categories that we call D0 and D1. And D0 represents the objects of our category, while D1 should represent the morphisms of our internal category. And what happened in this case is that D0 is a category whose objects are objects of D, and the arrows are arrows of D. While D1 is a category where objects are pro-arrows, so the vertical kind of morphisms, and morphisms are double cells. So these two categories have some relations. For example, we can go from the category D1 to the category D0 with this functor S that is the source functor, so the domain functor. So the idea is that we can take a pro-arrow and a pro-arrow from A to B, and S will give us A, the domain of the pro-arrow, while T will give us B, the target or codomain of the pro-arrow. And then we have identity, we have composition. So this structure of internal category really encodes all the data of a double category and all the axioms that we had before. Okay, so the first example of double category that we are going to see is the double category of sets and relations. So imagine that we have two sets. We know two different ways of relating these two sets. We can construct a function from a set to the other one, but we can also consider a relation between the two sets. And so with this data, we can really construct a double category. So objects are sets, arrows are just functions, while pro-arrows are relations. So a pro-arrow R from X to Z is a subset of the Cartesian product of X and Z. So this is a relation. And then we have double cells that will interrelate functions and relations. So a double cell of this kind is meaning that F times G of R is contained in S. So this filling alpha is saying that we have this property that if X and Z are in R, then F of X and G of Z are in S. So we have this kind of relation between the two. And the double categorical structure is really able to capture the interactions that we have between functions and relations on the sets. And if now we want to see maybe a more algebraic example of double category, we can consider mod, the double category of rings and bimodules. So objects are now unitary rings, and arrows are ring homomorphisms, the one that we study in algebra, while pro-arrows are bimodules. So a pro-arrow from M, from R to T, is an RT bimodule. So what is this? It is a group homomorphism from R times M times T into M, which is saying that we have two different actions on M, one action of R and one action of T, one on the left and one on the right. And these two different actions are compatible with each other. And now a double cell of this form is an FG equivariant group homomorphism between the group M and the group N. And it also has these additional properties. That is this property that is not so important. But the idea is that this structure of double category captures interactions between rings and bimodules. So two different structures that we want to study in algebra. Okay, and what we are doing in our project is we have introduced a new notion of factorization system for a double category. That is called the double orthogonal factorization system. So a double orthogonal factorization system is an internal category in the category of categories with factorization systems. So to define it, we are taking the internal approach to double category, the second one that I explained. And this is very natural to give definition in this way, but what is the meaning of this? Because if we read this, maybe we don't understand what it means. A double orthogonal factorization system is a pair of two different factorization systems. One is a factorization system on the category D0, so the category of objects and arrows, and the other is a factorization system on the category of pro-arrows and double cells. So this means that we can factorize both arrows and double cells in our double category. And these two factorizations that we have are compatible with each other, in a sense that that will be clear from the examples, hopefully. So let's see how we can define, for example, a double factorization system on the double category of sets and relations. So we said we need to factor arrows and double cells. So to factor an arrow, we just take the image. So we still use the surjective injective factorization system because arrows in this double category are just functions between sets. And then we need a way to factorize double cells. And remember, a double cell was a particular property of the relation R and S with respect to F and G. So it's that F times G of R is contained in S. And using the image of F times G, we can factorize this as the composite of two double cells. So we are able to factorize both arrows and double cells. And here we see the compatibility between the two factorization systems, because when we want to factorize these double cell, we need to have that on top here, we have the factorization. Oh, what happened? We have the chosen factorization of F. So this is the chosen factorization of F. And this is the chosen factorization of G. So the factorization system on arrows interacts with the factorization system on double cells. And we can also construct a factorization system on mod, so the other double category that we spoke about before. And in this case, we need first to factorize ring homomorphisms that are the arrows, and we still can choose the surjective injective factorization system for that. And then we also need to factorize cells. And if you remember, a cell was a group homomorphism between the bimodule M and the bimodule N with certain good properties. And so we can still factorize this group homomorphism as surjective and injective function. And we can use this factorization to factorize our double set. So the idea is that we are using twice this idea of surjective injective factorization system, but on two different algebraic structures, and they agree with each other. Okay, so these are easy examples. There are more complicated examples as well, but that we are not going to explore today. And now I want to speak a little bit about one of the main results that we have for these double factorization systems. But in order to introduce this result, we need to speak about monads. So a monad is a particular kind of functor, so it goes from a category to itself. And this particular kind of functor behaves like a monoid somehow. That's why the word monad. So what do I mean is that given a monad, given this functor, we have a multiplication for the monad and a unit for the monad. And the multiplication is given like this, so it's a particular natural transformation. So it's a way to relate T composed with T and T. And the identity is another natural transformation of, sorry, the unit is a natural transformation of this form. And this multiplication and unit satisfy the laws, the usual laws that we have for a monoid, that are now expressed in a categorical version. So this square is saying that our multiplication is associative. So if we first multiply and then multiply again, or if we do it in the other way, we get the same thing. And while these two triangles are saying that the unit really behaves as a unit in the usual sense. And these kind of functors are very nice and important because they allow us to encode the idea of action in a categorical way. So they allow us to view the idea of action in a categorical way. And this is thanks to the categories of algebras. So every time we have a monad, we can construct a category of algebras for each monad. An algebra for the monad T is a pair A alpha, where A is an object of the category and alpha is a morphism from T of A to A. And we need to think about of this as an action as a set equipped with a group action. So think of A as a set and think of alpha as an action of a group G to the set, on the set X, on set A, sorry. And these two diagrams that are satisfied are saying that this really is a group action. So this is saying that if we act on a product, we get the product of the actions. And this is saying that if we act on the identity, we get the identity action. But again, in a categorical way. And the morphism between from a pair like this to another one is a morphism from A to B that is equivariant with respect of the two actions that we are fixing on A and B. So we can see some examples of monads. So the first is the one that I was referring, the one I was referring to. So we can take a group G and we can consider this functor from set to set that takes a set and sends it into the Cartesian product with G. And now algebras of for these monads are sets equipped with an action of G. And morphisms are G equivalent maps. So we can capture this framework with a monad, but we can capture other interesting things with a monad. For example, the construction of a free monoid over a set. So we have a monad M that sends a set to the free monoid over these sets, and the algebras for this monad are monoids, the usual monoids. And we can construct other monads similar to this, so free construction monads. And we have a lot of different kinds of monads. So they are important because they are very nice functors, and they are also important because objects that are algebras for a monad have very nice properties. So it's very useful to prove that an object that you are studying is the algebra for a monad. And this has been done by Korostensky and Tholen for factorization systems. So Korostensky and Tholen found a monad that is called the arrow monad over cat, and it sends a category into the category of the arrows of that category. And this is a monad, and the algebras for the monad are exactly the factorization systems we spoke about. And what we managed to do is we proved that we can generalize this result for double factorization systems. So we can generalize the arrow monad from categories to double categories, and we still have that the algebras for this arrow monad are double factorization systems. And this gives us very good properties for double factorization systems. And maybe it also tells us that our definition of double factorization system is a nice one, a good one, because it comes from a monad. And that's everything I wanted to say. Thank you.
Thank you, Elena. It was really nice to learn about the work that you're doing from the Joint School. Are there any questions? It was my first time encountering the definition of the double category. I've never worked with them before. You define the arrows and the pro arrows, and then put in an alpha that represented a cell.
Yes.
Okay, and then I understood that you had double cells thereafter when you were working with factorization systems on there.
Yes.
Was that alpha in general? What's the intuition behind it? I might have missed it.
The intuition is that maybe that square is not commutative, but is filled with something.
Okay.
It might be, for example, a way of going between these two edges to the other two, for example, in some cases. It's kind of a morphism between these two edges and the other two, in some cases. Or in some other cases, is a property that this square has, a special one. There are different kind of frameworks.
I look forward to learning more about it from you. Yes, no problem.
A question about factorizations.
Yes.
I remember in topology, learning about a monotone light factorization of an arbitrary continuous maps. I think you have certain conditions of the domain and codomain. I can't remember. But the monotone one factor is the one that takes, where every fiber is connected. The light one is where every fiber is totally disconnected.
Okay.
And I was wondering whether those kinds of things have been studied generally.
I think so. I've seen something about the monotone light factorization system more general categorically or so we have not considered, but some people are very interested in this factorization system in the categorical frame.
Is it orthogonal?
Yes, I think so.
There are also weaker versions of factorization systems that don't have the orthogonality property, but we are considering the good ones with the orthogonality.
Before we end, I'll just mention that Elena's postdoctoral fellowship is in collaboration between Stellenbosch University and UKZN. So she will be spending a lot of time with us over the next 2 years. So we have seen her. Feel free to engage with her about the work you're doing to see if there can be any link. She's going to be here for the next 3 to 4 months before she goes back to Stellenbosch to do some work and then come back. And we're very pleased to have you join us at UKZN for the time that you're here. Okay, we'll thank Elena. There were no questions from the online audience, and now we'll all exit for a light lunch. Okay.